Ulrich Schneider from KTN. So I will start with my own introduction. I studied mechanical engineering master at the university in Hanover, and followed by 7 years as an operator, pipeline operator, at that time Preußag Oil and Gas, and later on positions in Pipetronics, BAI, NDT, and since 2014 with KTN as business development manager. So in total 36 years in the industry working with our pipelines. So my topic here, inspection of challenging pipelines, latest developments, and some case studies. Should use this one. So after a short introduction, I will show the KTN inspection solutions. It's UT, ultrasonic, for geometry, wall thickness, and crack. And second, it's Eddy Current-based technology as Eddy Current and SLOFEC, and that followed by 3 case studies. The first one is about a 42-inch loading line, which was inspected with ultrasonic, especially for weld cracking, long seam weld cracking. The second one and the third one are with Eddy Current and SLOFEC, and that is the gas vent line offshore with some corrosion problems. And the third one was a special topic, was a steel pipeline with an internal mortar liner, 10 millimeter. And we had a lot of inquiries for that, and we had to do a test for that. And then followed by some summaries, advantages, disadvantages, and a conclusion. So we all know that the worldwide pipeline network is aging, and we have to maintain its integrity, and we have to physically measure the condition of the pipeline. This is typically done since about 50 years with so-called intelligent picks. So normally conventional tools which go from A to B, launched at A and took out at B. So, but unfortunately, only some people say 50% of the network is designed as piggable. So therefore, easy calculation, about 50% is not piggable. And these pipelines are here visible on this picture. So that could be, for example, loading lines or risers offshore, any kind of short pipelines as you see here. They might not have a launcher or receiver, and there might be other things that they are not piggable. Of course, you can say with a bigger budget, more pipelines can be inspected. If the lines are modified, you can modify a pipeline, install a launcher, you can modify it, install a receiver, but that might be a lot of money, and you don't want to spend this kind of budget. Alternatively, special ILI tools can be used, and that is, for example, when you have on one trap or access from one side only, then the solution could be a bidirectional tool. Or if in addition you have no flow, let's say no pumps for a loading line, typically on the boat is the pump. If there's no boat you want to inspect, then you have no flow. And then the solution could be a self-propelled tool, that means with a crawler in the front. And this could be an autonomous tool, or typically it's a tethered tool, so a cable-operated tool. As you can see here on the picture, it's in the tray. You will see more detailed pictures later on. Could be, for example, a camera in the front if we are on the clear product, and then a crawler, and then maybe 2 modules with a measurement technology, electronic and data storage modules, and then a cable, a winch, and a control unit. So the cable has 4 functions. First is to get the power to the tool. Second function is to get the data real time to the control unit. Third function is to control the movement of the crawler, forwards, backwards, stop, and so on. And the fourth function is a safety function. That means if the tool gets stuck somewhere, then we can still pull on the cable with approximately 2 tons and get it out. So very safe. This is the difference between a typical tethered tool and a conventional ILI tool. A conventional ILI tool goes from A to B, so has cups, can only go in one direction. And typically it has also a flexible sensor carrier. This tool looks different. We have much less friction because everything is running on wheels. We have a lot of bypass, and we have a stiff sensor carrier. The beauty is that we can not only do wall thickness measurement with this, same as in the NDT presentation yesterday, we also do geometry measurement at the same time, so we can measure dents, ovalities, roofing with the same tool. So I will not touch this because this was explained in conferences and presentation 100 times. That's the vertical beam wall thickness measurement. But I will have a word with this because this was already mentioned yesterday also several times. That is coverage, but coverage, of course, is not the only important thing. Important is also the resolution of the measurement, which means, in principle, how many sensors do you have on the circumference and how many shots you do in flow direction or in working direction. So we have the best is 5 millimeter from one center of a shot to the next one, and 1.5 in axial direction. We can even go with 0.75 millimeter, so that's an excellent coverage. For this technology, for crack detection, shear wave, angular beam, this was also explained many times in presentations. I only want to point out here that this is a very excellent technology for detection of cracks, but less good for depth sizing. And therefore, we are proud that we have another technology on board as well, and that is TOFD, stands for time of flight diffraction. I think it's a well-known and well-used technology since many years in the industry as well, but less in intelligent tools, because here you have to stop the tool somewhere and start it with the scanning. Principle is we have a transmitter and receiver. We scan the whole wall, and we get the first signal from the lateral wave, that is from here. This is the first signal from the lateral wave, and the latest is coming back from the back wall. It's here. If we have something between, then these are signals from a crack. So we can quantitatively measure a crack with this technology. These are some pictures of winches we have. So, for example, we start with 500 meters. This is 1 kilometer or 10 kilometer. Longest one is 12 kilometer. But we have solutions as well for 24 kilometer. That is depending on the amount of bands we have to pass. A picture of the control unit. We always have a look on the data immediately, do pipe books and do check the worst defects already. And we control the crawler. And these are some further pictures about tools. You will see them later on in animations as well. In principle, we can cover 6-inch and up. These are crawlers, small diameters and the bigger diameters. You will see them better in the animation, how they move, how they bring the tool forward. This is something which is not typical for a conventional tool when you launch it. This is something you need when you have a cable-operated tool because we need a cable penetration into the launcher. And this is our stuffing box, flange with stuffing box. And that is something we bring to site. And then typically we don't have space enough for bringing the winch just behind the launcher. So therefore we use guiding wheels. And then sometimes we have, wherever it's spaced, the winch on the upper deck on the platform. And somewhere we need to guide the cable to the winch. This is a short summary of technologies we typically use. Most common is the ultrasonic pulse echo wall thickness. That's the vertical beam technology. So then second is the shear wave, creeping wave and angular beam. So that's the crack detection, full coverage. And then what I mentioned is ultrasonic TOFD for crack sizing. Then in principle, two eddy current-based technologies that could be the pure eddy current or the SLOFEC technology, which I will explain later on. If the product is clear, like water or naphtha, whatever, then we can use also a camera. And sometimes we even had a grinding machine on board. So that was used for grinding out an internal crack. And in another case, it was grinding down an internal girth weld penetration. So this is a short story about the loading line inspection, a crude oil line, 42-inch. The operator detected just by accident that they have some cracking problem along the long seam weld and some corrosion as well. And the line was not piggable at all, had no launchers. And fortunately, we could take out the piece here between two valves, and then we prepared a shorter valve for the launching. So in principle, then you can go from here to the right and also to the left. And here you see the complete tool, which is in the front. The blue one is the crawler, followed by the TOFD unit and the wall thickness measurement unit. This is all prepared after a site visit and launched. And you see already that the winch is placed on the side, and then we need a guiding wheel to bring the cable to the winch. So now they are installing this magic flange with a stuffing box. Actually, I can tell you it takes a few seconds longer than it's shown here in the animation, but it's good enough. So the winch we have with ATEX certificate, and the tool is only switched on when it's filled completely with crude oil, so no problems with ATEX. When it's completely filled, then the crawler starts moving, and then we immediately also collecting data and do data analysis because we have real-time data. So this symbolizes the wall thickness measurement. You can see that we immediately see also the girth welds and the long seam weld. All these locations are noted because on the way in, we do wall thickness measurement. On the way back, we do wall thickness measurement again. And on the way back, we stop at the right positions to do TOFD scan on the long seam welds in this case. So this is a nice trick that the cable is always in the center. It's patented to reduce the friction. I think nobody believes that, no? This is, of course, a stupid animation. So unfortunately, the cable is not in the center, and we have some friction in bends. So now the tool is coming to the end of the pipeline, stops and goes into return mode. And now we stop at the right locations at the girth weld, and then we locate the long seam weld position and scan the long seam weld. So that means up to the end of this pipe spool. And then we stop again, and we find the location of the next long seam weld and do the same thing. And I will just go to the next presentation, our next slide. I will talk now about eddy current and SLOFEC. SLOFEC stands for saturated low frequency eddy current. So principle of the SLOFEC is we have a magnetizing yoke. We have permanent or electromagnets here, and we generate a magnetic field, an alternating DC field in the pipe material and the wall. And in addition, we have eddy current coils here, and we create another field here, which is superimposed to the first one, a little bit weaker. And with this eddy current sensors, we can measure the permeability on the field strength applied by the magnet. You will see it on the next slide, where we have a defective sample. So here's a pit corrosion, and you see that the magnetic field lines are compressed. And going from left to the right with this arrangement here, these eddy current sensors will pick up the change of the relative permeability, which is dependent on the change of the field strength due to the reduction of cross-section. So when you ask about the specification, we can say the specification is very similar to standard MFL. Let's say the threshold for the minimum depth is about 10% of the wall thickness, and the depth sizing accuracy, the tolerance, is also about plus minus 10%. Here you see a picture of the tool itself, of the sensor carrier, and here about the complete tool. It can be 3-4 meters, depending on the amount of equipment we carry here, like the camera, 1 or 2 crawlers, and then the SLOFEC sensor carrier and other modules. So this is the next technology, the principle of eddy current layer thickness measurement. So we can say when the coil comes closer with its alternating field to an electrical conductive material, which is this one, then it is creating an alternating current, which is called the eddy current. This current creates again an electromagnetic field, which is in the opposite direction and which weakens the original field. And the effect to the coil is a change in its inductivity, which is a characteristic property of each coil. When you see what we do in a pipeline with a mortar cement liner, which is about 10 millimeter, and we have these eddy current sensors here in the sensor carrier. They are spring-loaded, so we are always in contact with this mortar liner. So what the sensors are measuring is the distance A1. That means from here to the steel. So here, the normal 10 millimeter, here maybe 8 millimeter because some cement mortar liner was broken out. Here, the normal 10 millimeter, and here even up to here because this is the gap we are measuring up to the pipe wall. So we see even internal corrosion with this technology. So this is a short story about a gas vent line, 10-inch offshore in the Far East. They had a corrosion survey which was they were obliged to do a corrosion survey from the government. The line was not designed piggable and was, of course, never inspected. And what we did was a test before because the pipeline operator was concerned about maybe some debris in the pipeline and the tool could get stuck, and therefore we did some testing about the pulling forces, and we found out that with the same configuration of bends we had here, we did some testing that to pull the tool in and out, the pull-out forces are just 1/3 of the pull-in forces, so we were quite on the safe side. And the nice thing, and one of the reasons why the customer chose this technology was that the SLOFEC technology is not sensitive for any debris in the pipeline. So, and then a third function was that when you switch off the power, then I think you can easily pull out the tool. That is different to, let's say, a tool with permanent magnets or a magnetic flux tool. And of course, an ultrasonic tool couldn't be used because there was no liquid in the pipeline. So we launched the tool. They expected some external corrosion in the splash zone and also some internal corrosion at the bottom, which we finally also found. But we did the whole inspection within one shift successfully, and we could do some data evaluation immediately. And finally, we did a complete report, and the final results were that we had maximum 28% defect depth maximum, and the ERF, the pressure ratio, was far below 1, so there were no immediate repair necessary, and the customer was happy. So I will go just straight to the next one, which shows some pictures from the platform. Of course, typically on these platforms, everything is very tight. It's difficult to get some place for the tool preparation. So the tool is laying here on the tray, and the launching was just a little bit further to the left. You can see here the cable and the guiding wheel, and so we launched in vertical position. Was also difficult to find some space for the collection of laptops because we used just 2 laptops for the 2 movements of the crawlers and then additional ones for data analysis. And this is the next one. It was about a mortar liner in a 12-inch steel pipeline. We got a lot of inquiries for something like this, and there was no real solution for that before. And we thought a combination of eddy current and SLOFEC would be ideal because with the eddy current, we could measure the layer thickness of the mortar liner and even the internal corrosion in the steel, if there's any. And with the SLOFEC, we can measure the steel wall behind internal and external corrosion. So we built a test pipeline in Kontrolltechnik, Germany, and with 1.5D bends, a lot of artificial and natural defects, different sizes and depths. And the KTN crawler pulled the combo tool through the line and back. and all defects were detected and sized according to the specification, most of them plus minus 10%, the worst plus minus 20% of nominal wall thickness. And this was picture from a test pipeline and the tool itself. And more important, maybe to show some of the defects we produced here, and then even more relevant, how we saw that was the depth evaluated by the SLOFEC technique, and that was the depth mechanically measured. And we did a lot of testing with epoxy coating, thick epoxy coating, not 600 micro or something, but 10 millimeter, and also cement mortar 10 millimeter. So at the end, we could say this inspection was feasible and was successful. And so now we can offer 8 to 18 inch at the moment with a maximum of wall thickness 16 millimeter. This depends a little bit on the diameter in general, and a maximum coating thickness of 10 millimeter. So both can be inspected in one with this combo tool. So the thickness layer measurement of the epoxy or the mortar liner and the steel behind. And if we are in a dry line, that could be about 1,000 meter. We did some smaller reference projects as well, could be maybe a little bit longer. It's also depending on the configuration of the bends and things like that. And if we are doing the same thing in water or anything, then of course we could go 10, 12 kilometer anyway as well. So advantages of the eddy current method in mortar liner, real thickness layer measurement, and surface roughness has only minor influence on results, and metal loss under mortar liner will be shown as well. And here are the main SLOFEC features and advantages. The method does not need direct coupling with surface, so it can be used in dry medium or in multi-phase. Requirement for cleaning is very low because of non-conductive and non-magnetic layers. Debris do not influence the signal, and the detection of defects through relatively thick and non-conductive and also non-magnetic coating layers as epoxy, mortar, etc. is possible. Also usable is this technology for non-magnetic cladding. It could be stainless steel or aluminum, or by evaluation of the phase information, the defects can be also differentiated between internal and external. So as a conclusion, we can say there are inspection solutions available even for pipelines without traps and pumps. The solution is a self-propelled bi-die tool. Depending on the product, different technologies can be used. For liquid lines, ultrasonic. For geometry, wall thickness cracks. For gas lines or multi-phase lines, we have eddy current and SLOFEC. So even for thick internal coating, carbon steel and aluminum. So, and this is, thank you for your attention.